Let's move on to the next slide. So before we get started with the nitty-gritties of our topic, I'm gonna review some of this important terminology. Or for those of you who are new to it, that's fine as well. We'll go over each of them with detail. So first term you need to know is a polygon. Polygon is just an enclosed shape with straight edges. Another word term for edges is sides, but usually we use the word edges in math terms. Second term, the perimeter. Perimeter is basically like the total length of a polygon's edges. So say you have a square with like 4 edges. Basically, when you add up all those 4 edges, that'll give you the perimeter. Fairly straightforward. The third term we have here is the area. Area is basically the shape enclosed within a polygon. So say you took the square again, and basically the area is just the space, like the area inside the square. I use the word area in there, but like you get what I mean. And there's usually always like a formula to calculate the area of like a specific polygon. So like for a square, you just multiply a base by its height. And then the final term, an angle. Angle is basically a measure of the space in between two edges that intersect at a vertice. So vertice is just a mathematical term for a point. So say you have two edges like this, you want to measure the angle in between, just like that. Any questions about these terms before we move on? If there are no questions, I'll move on. All right, so let's look at a review of what circles are. Hopefully none of you are new to this. You should know what a circle is. But let's review it. So a circle is basically a polygon with an infinite number of edges. So circles, we don't say like one curved edge, right? Because like edges of a polygon, remember polygon has to have straight edges. A circle is a polygon, but we're assuming that the number of straight edges is infinite. So like each edge is like really, really small, but they add up when you like combine them together to make a circle. It looks like it's just one curved edge. But in reality, it's just an infinite number of straight edges, right? And then the circle's perimeter, so when you add up all those edges together, take the sum, it's called the circumference. So circle's perimeter is called the circumference, right? And then each point on the circumference is equidistant. So equidistant is another term for same distance. Each point on the circumference is equidistant from the center, the center of the circle. So you know, like right here for this circle as an example. And then this distance is called the radius. So point from the circumference to the center of the circle is called the radius. Right? And then the area of a circle is this formula pi r squared. Hopefully you guys know what pi is. It's a special decimal number. So area is pi r squared, and then circumference, so remember the perimeter of the circle, is 2 pi r. And these terms are like multiplied together. Any questions about this slide? Right. Hopefully that was a review to all of you. So let's move on. We're going to look at some special side lengths of circles. We don't have to know all of these. I think there's only like one or a few that we'll be using in this lesson. But so let's look at, remember the radius? Radius is just the distance between the center of the circle to a point on the circumference. So see, this is the radius, and then you also have this other yellow line. So these two yellow lines are the radii of the circle. Next side length you need to know is the diameter. Diameter is just a line that connects 2 points on the circumference. The 2 points on the circumference are its endpoints, and it also passes through the center of the circle. And you guys may notice the diameter is twice the length of the radius. Like this is one radius, and then this is another radius, and you add them together to get the diameter. Right. And then we have some other side lengths. You guys don't really need to know about these, but it's good to know. This one right here, it's called the chord. A chord is just, it's like a diameter, except it doesn't pass through the center. So it has two endpoints on the circumference, but it does not pass through the center. Otherwise, it would be called a diameter. So that's what a chord is. You see there? And then now we have a secant line. A secant line is just a line that just passes through the circle, but then it's outside of the circle as well. So the secant line passes through the circle at these 2 points. It has to pass through 2 points. But it also extends outside of the circle. So that's what how a secant is different from, say, a chord. Right? And then the last special sign length. This one's a bit more important. So this is called a tangent line. So a tangent line is like a secant, except it only intersects the circle at 1 point while it's like fully extended. So you can see right here, the tangent line only intersects the circle at this point right here and nowhere else. Right? Any questions about these side lengths? All right. If there are no questions, I'm going to move on. Right. So let's look at what an arc is. An arc is a portion of the circumference of a circle. So if we look at this diagram right here, we have this arc right here. They labeled it as L. So that's what an arc is. It's just like a fraction of the circumference of the circle. You're only taking a piece of that circumference. Right. And here we have some other terms relating to the arc. So we have an arc measure. Arc measure is basically the angle measure of an arc. So what that means is that you're measuring the angle. So say look at this diagram. So an arc is formed by these two radiuses, or radii, sorry. An arc is usually formed by two radii, and then that's where the arc is. And it's basically you're measuring the angle between those two radii. Here they labeled it as theta. This symbol is called theta. That's what they usually use for measuring angles. And then next term we have is the arc length. This one's pretty straightforward. It's basically the length of an arc. So over here, it would just be L. L is just the length of the arc. And then we have a formula that relates arc length and arc measure right here. So basically what this states is that the ratio between arc measure and the 300 full rotation, or 360 degrees. So arc measure divided by 360 degrees is equal to arc length divided by circumference. And you guys can probably understand why. So 360 degrees, so like the denominator for each of these fractions, so 360 degrees, that's a full rotation. And circumference as well, you can also think of that as a full rotation as well. And then arc measure divided by 360 degrees. So that means arc measure divided by 360 degrees would equal your arc length divided by your circumference, because these are fractions. Like arc measure is a portion of the 360 degrees, and then arc length is a portion of the circumference. So that's why these two fractions or ratios are equal to each other, right? Any questions about this? And we'll go over an example about how to use this as well in next few slides. Right, no questions, I'm going to move on. Just we're going to learn about what a sector is. So a sector is basically a portion of the area of a circle. You can see that's enclosed by an arc and then the two radii. Right? But this is a measure of the area, not like what circumference is or like what the angle is. We're actually calculating the area of that section. It's called a sector. And yeah, said here, it must be touching the center. And some common examples of like names for sectors include like semicircle. Semicircle is just half of a circle, half of the area of the circle. We also have quadrant. Quadrant is 1/4 of the area of the circle. So these are some common sectors you should know about. And basically the formula for the sector area, it's fairly straightforward. It's just, so area is equal to arc measure divided by 360. I think my headset stopped working for a sec. Yeah, okay. I think we're back. Sorry about that, technical issues. But so we were looking at the area, sector area formula. So this area is equal to the arc measure divided by 360 degrees. And you multiply that by the formula for the area of a circle, which is pi r squared. It's fairly straightforward to understand because like you're taking a fraction of that entire area of the circle, and then that fraction is equal to whatever your angle is for that arc or sector divided by the full rotation of the circle, which is 360 degrees. Right? Any questions about this slide or from the slide before? Any questions so far? Okay, if there are no questions, we're going to move on to a problem where we apply this. All right, so here's a problem. So for a circle with a radius of 12 centimeters, what is the arc length and sector area for an arc measure of 120 degrees? So an arc that has like an arc measure of 120 degrees is what I mean. I'll give you guys a minute or so to think about this. And if you have the answer, you can unmute yourselves or also type in the chat. So, does anyone have an answer so far for these two questions? For arc length and sector area. I think we'll just take this up. Yeah. Let's see. All right, yeah, let's just take this up. I'm going to share a whiteboard to you guys. So this is where we're going to take up the question. I'll use this as well for the other questions that we encounter later on. So yeah. So question was, we have a circle with a radius of 12. We just put that down, r equals 12. And we want to find its, what is it? The arc length and the sector area. 12 centimeters, that's the units. Oh yeah, and we're given that the arc measure. So remember, this is the symbol called theta. It's the usual symbol that we use to represent angles. It was 120 degrees. Right. So what should be the first step of this question? We should probably calculate the area and circumference of the circle because we need both of those for arc length and sector area. Well, we need area for sector area, and we also need circumference for arc length. So let's do that first. So here, let's calculate circumference first. Circumference is just 2 pi r. So this is 2 pi times 12. Put 12 in brackets. Right, and we can multiply 12 by 2 to get 24 pi. Yeah. And we're going to keep it as an exact answer. We're not going to actually like multiply 24 by pi and calculate that decimal value. Just keep it as pi. Let's calculate the area as well. Mention that. So that's just pi r squared. So pi times 12 squared. Let's write that formula down. So this is 12 in brackets. So we're substituting 12 in place of r. And this will give you 144 pi. Right, so now we have circumference and area. Now we need to calculate arc length and sector area. So let's try to calculate our arc length. Right. So arc length is, remember, it's just like a fraction of the circumference of the circle, right? So we want to know what that fraction is, right? And the way we do that is we use the arc measure and divide that by 360 degrees. So arc measure is 120, and full rotation is 360 degrees. So this will give us a fraction of the circumference that we want, right? And this is just equal to 1/3. So this means that the arc length is just 1/3 of the circumference of the circle. So that means we can just multiply circumference by 1/3. So just do 1/3 times 24 pi. And cross multiply 24 of 3 to get 8 right here. And this will just leave you with 8 pi. Right, so that's our arc length. I'll use a thinner pencil to get our sector area. It's going to have some more space for us. So sector area is a similar thing. We need to calculate the fraction. Well, we already did that. It's just 1/3. So if arc length was a 1/3 of the circumference, that means that sector area is 1/3 of the area of the circle. And so to get sector area, we'll just multiply 1/3 by the area, which is 144 pi. Right, and if you cross multiply, this would become 48. And so then the final answer for your sector area would be 48 pi. Right, so 48 pi sector area, 8 pi is your arc length. All right, any questions about this problem? Does anyone have any questions? Or anything you're confused about so far? Okay, let's go back to the slideshow. And let's look at triangles. So we focused on circles, now let's go to triangles. So let's review what triangles are actually. Hopefully you all know what a triangle is, but we're just going to review what it is. Triangle is basically a three-sided polygon. It has 3 sides. And where the interior angles, so the angles inside the triangle, add up to 180 degrees. Right? And then there's 3 types of triangles. You guys remember these? We have first an equilateral triangle. Equilateral triangle is where like all sides and angles are congruent. Congruent just means equal in measure. Like all sides are equal to each other, and all the angles are also equal to each other. And the angles of an equilateral triangle are always set to 60 degrees. So if you see this diagram here, this is what an equilateral triangle looks like, and you see all angles have to be 60 degrees, right? 180 divided by 3. Next, we have an isosceles triangle. An isosceles triangle is where you have exactly 2 sides and angles that are equal to each other or congruent to each other. Seeing this diagram here, this isosceles triangle, so it has these 2 sides that are equal. They're usually marked with tick marks, like this. And then we have 68-degree angles on this side and on this side. So those are 2 angles that are congruent to each other. So that's an isosceles triangle. And finally, we also have scalene triangles. Scalene triangles are where no sides or angles are congruent at all. So you can see in this diagram right here, So you see this side has 1 tick mark, this side has 2 tick marks, and then this side has 3 tick marks. So it shows that none of them are equal to each other. And you can also see that the angles aren't equal to each other as well. You have a 61 degree here, you have 63 degrees here, and if you calculate this angle right here, you know that it would not be equal to any of these two, right? Any questions about this before we move on? If there are no questions, let's move on. Okay, so if you remember the area of a triangle, it's usually this formula of base times height divided by 2. So I put here is BH divided by 2. But what happens if, say, you're only given the 3 side lengths of the triangle, and you're not given the height as well? And here's an example. Say you had the triangle ABC, where you were given side lengths A is equal to BC. You also have side length B right here, which is AC, and you also have side length C right here, which is equal to AB. So from here, how would you calculate the area of the triangle? Well, there's a special formula that we can use, and it's called Heron's formula. Heron's formula, sorry. And this is what it looks like. So we have the same triangle, like the similar triangle of ABC, side lengths ABC. And so this is what the formula states. So we have the area of a triangle equal to the square root of this product. And so let's break it down. So in this product, we have S. What is S though? So to explain S right here, S is equal to A plus B plus C. So that's the perimeter of the triangle. And divided that by 2. So this is basically like half the perimeter of the triangle. That's what S is. Okay. And so that's S, and then that's one. That's a term of one of the product. That's one of the terms of the product. And you multiply that by S minus A, and you also multiply it by S minus B, and finally S minus C. So this is Heron's formula. And the proof for this is actually pretty complicated, so I won't be showing this to you guys today. But you can search it up yourself and try to see if you can understand it. There's like a geometric proof. There's also an algebraic proof that you can search up. But yeah, it's pretty complicated to show you guys at this moment. But are there any questions about this formula? Any questions about this? All right, no questions. All right, now we're going to use this formula in the problem in the next slide, right here. So find the area of a triangle that has side lengths 4, 5, and 8 using Heron's formula. I'll give you guys a minute to solve this. And if you have the answer, just unmute yourselves and say it, or you can type it in the chat. Anything works. Does anyone have an answer so far? Just curious. Probably should have changed these numbers to make it nicer, because like some of these isn't divisible by 2. So yeah, it's a mistake on my part, but still solvable. Yeah, let's just take this out. Substitute the numbers to the formula ourselves. So let's get a new whiteboard and let's solve this. All right, so I'll rewrite the formula right here, just for reference. So we have S times S minus A times S minus B times S minus C. All right, and then we have S. Remember that S is half of the perimeter of the triangle. So A plus B plus C, all of that divided by 2. Just like that. All right. And basically, to solve this problem, we just do some simple substitution. So let's first solve for S, though. That'll be simpler. Solve for that first. I'm just continuing it down here. So let's just pretend A is 4, B is 5, and C is 8 from the question. So 4 plus 5 plus 8. And if you solve for that, you would get, so what's 4 plus 5 plus 8? That should be 17. 17 divided by 2. And we're just going to keep it as this improper fraction. Not going to change it to decimal or anything. All right, so now let's solve for the actual area now. So now we're just going to substitute this value of S and also A, B, and C into the equation. Sorry, the formula. So S is 17 over 2. And then we're just going to substitute S minus A, S minus B, and S minus C. So 17 over 2 minus 4. Yeah, I should have probably chosen nicer numbers for these. So product is going to look a bit ugly, but we'll figure it out. All right, so now let's try to simplify whatever is in the brackets. So here we have 17 over 2 times, what is this, 17 over 2 minus 4. If you do this in your head, well, you convert 4 to 8 over 2, and you just do 17 minus 8. So I gotta give you 9 over 2 times, this should give you 7 over 2, 7 halves, and then this would equal to 1 half. Yeah. And so now you just multiply, there's nothing to cross multiply because the bottom is just 2's and then there's these odd numbers at the top. So we're just gonna multiply numerator to get your numerator and then just multiply denominator numbers by your denominator. So it should be something over 16. I'm not sure what this is equal to. Does anyone know what this is equal to? So 17 times 9 times 7 times 1. Does anyone know what that is equal to? Like if you have a calculator on your side. Or if you can do it in your head, it's also pretty impressive. Yep. I'll calculate it myself using my own calculator. So 17 times 9 times 7. What is that equal to? 1071. All right. I'll just double check because why not? Yeah, 1071 over 16. And so this is your final answer. And if you guys know how to, there's a technique called simplifying radicals. It's basically like you're making the number inside the square root a bit smaller, like making it more simplified. And so basically how this works is like you're trying to take out, like you're trying to make the number inside the square root more simple, and also you're going to have a number outside the square root as well. So that's how that works. Basically the technique is that like you're trying to find any perfect squares that divide evenly inside this number. So either 1071 or 16. And 16 is actually a perfect square because it's 4 times 4. So you can simplify this to square root of 1071 over 4. That's what this simplifies to, like that. Right? We don't have to focus too much on this. Just having this as final answer is fine as well. Any questions about this? All right. Hopefully that was a very straightforward question. You're just substituting in these values, 4, 5, and 8 into the equation. Okay, let's move on to another concept. So let's look at something called the end circle. So now we're back to circles. But we also have to combine it. We're combining this with triangles as well. So what's an end circle though? It's basically a circle that is inscribed in a triangle, where like all the sides of the triangle are tangential. So remember we learned about the tangent where it only intersects, a tangent line to a circle where it only intersects a circle at one point. So here all 3 sides of the triangle, so you see in the diagram here, all 3 sides are tangent to the circle at 3 different points. So that's what an end circle is. It's inside a triangle. And it has to be this exact like size as well. Can't be anything smaller or larger for this specific triangle. Right? Oh yeah, also that's the point. And then the radius of an end circle. So say I took the point from the center over here to say this point right here, or just another point on the circle, really. So radius of an end circle is called the end radius. In radius. Right? Any questions about this before we move on? Okay, if there are no questions, I'll move on. So now, how do we calculate the end radius of a triangle, given its 3 side lengths? We're actually going to use Heron's formula, actually. And this is what the formula looks like. So R, this is your end radius. So this is just equal to, remember Heron's formula? This is just the area of the triangle, where you have S times S minus A times S minus B times S minus C. And then you divide all of that by S, where S is, as from Heron's formula, is just half of the perimeter of the triangle, A plus B plus C divided by 2. So, and we're actually going to prove this formula, actually. It's easier than proving Heron's formula by itself. But so we're going to prove this formula, but first let's use another concept. So we're going to use this tangent line theorem right here. So you might have seen this in that diagram we saw a couple slides ago. Might have noticed it like slightly. But tangent lines are always perpendicular. Right. Sorry, might cut off again. Hate when that happens. But yeah. I think I'll switch a new headset for next time. But yeah. So a tangent line to a circle is always perpendicular to the radius of a circle. That's one of the properties of a tangent line. So like it intersects a circle at one point, but it's also perpendicular to the radius. And it has to be this specific radius where it intersects the tangent line. So here I said P is equal to 90 degrees, like that. And so with this property, now we can prove the end radius formula. So I'm going to go to the whiteboard and prove it to you guys. Any questions about this though so far? Before we go to the proof. Hopefully you had time to absorb that. Let's get to the proof. So let's draw the diagram first. Your edge, like that, and like that. Oh, that's ugly. A bit better. No, that's not too good. There we go. Okay. And let's try to draw the inner circle. So it'll look like this. Something like that. And it intersects the triangle at these 3 points. These 3 points right here. All right. And we're also going to name the triangle side lengths. So let's call the bottom one lowercase a. I'll also name this one b. And then we'll name this one c. Okay. So now what do we do from here? Oh yeah, so actually let's write down the formula just for reference. So remember it was just, instead of Heron's formula, I'll just write area of the circle. Because Heron's formula gives you the area of the circle in the first place. R divided by S, where S is equal to A plus B plus C divided by 2. All right, so what do we do from here though? So let's take a closer look at the diagram actually. Let's draw out the points, the circle center right here. Now from this circle center, we're actually going to draw three in radii. So one that connects the center to side A, like that, side A. I was going to connect the center to side B, like that, and finally to side C as well. So since these are all radius of the circle, they're all equal to each other. So I'm going to use tick marks to indicate that. Label one as R. Okay. And so remember the property of tangent lines that not only intersects the circle at one point, it's also perpendicular to the radius. So I guess I'll use this right here. Mark that as a right angle. I'll also do it for here. Do it for side C and then side B as well. So these are all right angles. All right. Now what I'm going to do is I'm going to connect the center to each of the 3 vertices of the triangle. So I'm going to do this. So that's 1. That's 2. And that's 3. I cover the R, so let's put it right here. Okay. So now I drew 3 lines from the center to each of the 3 vertices. And don't make the mistake that these lines form like a straight line with the in radius. These in radius and this line right here, they're not a straight line. It's actually an angle, slight angle. But, so now what do we do here? We can actually look at some smaller triangles than this large triangle. So the triangles that we're going to look at, I'm going to label these in yellow. So we have this triangle right here. So that's one of the smaller triangles. Let's label another one in green. This one has side C now. So that's another triangle. And then we also have a triangle right here for angle B, side B, like that. So notice that the area of each of these 3 triangles add up to the total area of the larger triangle. Right? So we're going to use that in our proof actually. And it's pretty easy to calculate the area of these 3 triangles, like individually. If you notice for the yellow triangle, it has a base of A, and we also know its height. Its height is R, or the in radius of the circle. Because like this height is always perpendicular to the base. Just remember that. And so we have R, which is perpendicular to A, and extends all the way to the top vertice. So therefore R is the height. Similar thing for these 2 other triangles. So the blue one, we have base is b, height is also r. For a green triangle, base is c, height is also r. So now we can calculate the total area of this entire triangle. Let's write it down right here. So area of the triangle, this would be area of the yellow triangle. So this is just a times r divided by 2. That's messy. And we're going to add the area of the blue triangle. And finally, the area of the green triangle. So these are very similar to each other. So like that. Base times height divided by 2. Yep. And let's try to factor some terms out. So the term we can factor out here is r. We can also factor the denominator out. So this would just be, we'd be factoring r divided by 2. Actually, no, let's not do that. Let's only factor r. Why? Oh, first let's actually combine these into one entire fraction. So AR plus BR plus CR from in your numerator divided by your denominator, which is 2. So let's do that first. And now let's factor R. So if you factor R, so basically taking the distributive property, dividing all these terms by R, you get R times A plus B plus C, all that divided by 2. Right? Now what you'll notice here is that, I'm going to write right here, writing a bit out of space. We can separate this 2, so this denominator of 2 for A plus B plus C divided by 2. Put it right here. So I just took the R out and then just had this A plus B plus C divided by 2 as the fraction. What you'll notice here, so remember we have S is equal to A plus B plus C divided by 2, or half the perimeter of the triangle, the entire triangle. And so what we can do here is just substitute this fraction for S. So we'll substitute S in here. So this means that the area of the entire triangle is equal to the in radius times the half the perimeter, so R times S. So now we have this. Now we can prove this formula right here. And it's fairly straightforward. Let's write right here. We'll rearrange it. Okay, so we have area is equal to R times S. This would mean that if you divide both sides by S, you would get R is equal to A divided by S. So the area of the triangle divided by half the perimeter. And we'll do it right here. We'll substitute in Heron's formula into A. So this would just be S times S minus A times S minus B times S minus C. And all that divided by S will give you your in radius of the triangle. I'll put like this is equal to R. All right, so this ends the proof of that formula. Any questions about this? You don't have to like memorize it. It's just good to know. Like it's really good to know like where your formulas come from, right? You don't want to just like use a formula and then you're just thinking about, oh, where did this come from? Like, how do I use it? Right? The proofs will help you understand that part. So that's why it's good to prove formulas whenever you can. So yeah. Any questions about this? Like the proof or the formula itself? Let's go back to the slideshow. All right, if there are no questions, we're gonna end off the lesson with a couple of problems for you guys to solve. Okay, this should be a simple one. We're just substituting in these values. So find the in radius of a triangle that has side lengths 10, 12, and 16. we'll just take up together actually. So we're a bit short on time. Okay. So let's write down the formula again. What were you given? So we need to find the in radius of that triangle. So remember, this was a formula because we were given all three sides of the triangle. And we have to use Heron's formula to calculate that area. And we also have this divided by S. Write down S again. All right. So this is a fairly straightforward problem. We're just substituting in the psi length values for A, B, and C. So let's calculate this down here. So first psi length was 10. The second one was 12. And then the final one was 16. All that divided by 2. Now if you calculate this, you should get 38 divided by 2. And that's equal to 19. So it's a good thing we simplify that. All right, so now let's substitute all these values into here, into the equation for R. Right down here, actually. So 19 times 19 minus 10, and then 19 minus 12, and then 19 minus 16. Just write all those down. All of that divided by S. So S is 19 itself. All right. So and this would just be equal to 19 times a bunch of numbers. So we have 9, 19 minus 10, times 19 minus 12 is 7. And 19 minus 16 would give you 3. All of that over 19. And then if you calculate whatever is in that square root, let's do it quickly right here. You should get this number. So 3,591. Yeah, over 19. You can probably simplify this radical, but I won't show it right here. All right, so this would be the value of your in radius. All right, any questions about this? About this problem? All right, if there are no questions, let's go on to a few more problems. I have 4 problems actually right here, but we're just only going to do a few of them. Choose. All right, let's just do this one. Actually, no. Let's do this one. This one. My bad. Yeah, this one. Okay. So the in radius of an equilateral triangle is equal to 2. Find the length of one of its sides. I'll give you guys like a couple seconds or a minute to think about it. So after this, we're just going to solve one more problem and we're going to call it a day. It's a bit short on time. I think we started late as well, so I'm just going to go a bit over time if you guys don't mind that. Oh, sorry, I wasn't sharing the slideshow, was I? Okay, sorry about that. I didn't share the slideshow. Okay, so here's the problem. The in radius of an equilateral triangle is equal to 2. Find the length of one of its sides. I'll let you guys think about it for a couple seconds. And just like understand the question. You don't have to solve it. Like think about like how you would try to solve it actually. Oh. So Yifan asked, do you share the slideshow with us after class? Yes, I will. I also share the slideshow on Google Classroom. Of course I will do that. I'm just gonna, okay, let's take this problem up. Let's go back to the whiteboard. All right, so in radius is equal to 2 for an equal out triangle. So in an equal out triangle, we have all the side lengths that are equal to each other. Let's just call it x. Actually, yeah, called x. Let x be one of the sides. Okay. So we want to find the so the in radius we're given is equal to 2. We're gonna have to use that in radius formula. But first, let's calculate. Remember, the in radius formula had a variable named s. Let's calculate what s is. So like half the perimeter of the triangle. So this would just be x plus x plus x. All of that divided by 2. We can simplify this. So we just add up all the x's together. So hopefully, guys, you know how to add up variables. This would just be 3x divided by 2. All right, so we have that. Now let's use our in radius formula. So actually, I'll just write it up right here. So this is s times s minus a, s minus b, s minus c. All of that divided by s. All right. So we're going to substitute some values into this. So this is just 2, r is equal to 2. And then we have s. This is just 3x minus 2. Sorry, it's 3x divided by 2. And we have 3x divided by 2 minus x. And for simplicity's sake, I'm just going to cube this. It's going to take it to the power of 3. Because we're going to have this 3 times. So s minus a, s minus b, and s minus c would all equal to each other. Just because, so we have s and for the first term, and the second term would always be x. Because like because this is an equal out triangle, all the side lengths equal to x. So then we have that. We have it 3 times, so it's y, take the exponent of 3. And then we divide by s, which is 3x divided by 2. All right, so let's simplify the top part. I'm going to move this 3x divided by 2 to the outside, not into the fraction anymore. All right, so then you can simplify this part in the fraction to be x over 2. And this is just divided by 3x over divided by 2. Okay. And basically we're just solving for x now from this equation, from this point on. So this will give you 3x. I'll simplify this in one step. So this is just x cubed over 8. So that's just 3x times x cubed. So if you know how to multiply variables together, you just add up their exponents. Well, they have to be the same variable, of course. So this is just 3x times x cubed, which give you 3x to the 4. And on the bottom, we have 2 times 8, that would give you 16. And we also have this 3x divided by 2. And what we're going to do there, here, I'm going to erase this part. We're going to make into a product instead of a quotient. So this would just be multiplied by 2 over 3x. Okay, I'm going to continue it over here. So it's 2 equal to. We can simplify some parts in this square root. So we can't simplify the 3, but we can simplify the x to the 4 divided by 16. So we're just going to move square root 3 out of here. And if we take the square root of x to the 4 divided by 16, we would get x squared over 4. So square root 3 times this fraction, x squared over 4. And then we have this on the bottom. We have this afterwards. So 2 divided by 3x. All right. And then we're just solving for x. We'll get rid of an x from here. So this would just be normal x. And then this x right here would be gone. So now this is a lot simplified. So this would just be square root of 3 times 2. Actually, right, forgot to cross multiply this. So this will just be 1, and then we have 2 over here. So this is just square root 3x divided by 2. And we have this 3 down here. So 3 times 2 would give you 6. And if you solve for this, so basically just multiply this fraction by its reciprocal. So multiply 2 by 6 over square root 3. So it then means you would get 12 over square root 3 as your final answer. Okay, sorry, that took a while. Okay, so then this is your final answer for the sine length of the triangle. All right, any questions about this? And don't think we have time for another problem. So you guys can try to solve it on your own time then. I'll post a slideshow on Google Classroom. Any questions about this problem?